work in which the principle would be correct. Later on, of course, once there was a relativistic theory of particles, and this rule here became part of the logic, inescapable logic, then there was a derivation of the equivalence principle, the exclusion principle. He was trying at first to describe an empirical fact. Of course, once he realized this, that there was such a nice mathematics to it, undoubtedly he started looking for deeper reasons for the mathematics, and eventually he found them. He and Dirac and Einstein were the people who really built this, and Bose, and Fermi, I suppose. I don't know if, for the life of me, Fermi was a very, very great physicist who did anything. Excuse me, Giorgio, I don't want to insult the Italians, but there he is. But I really don't understand what he had to do with any of this. Okay. Giorgio, your homework is to find out what Fermi did.
So for a single particle, essentially swapping two distinguishable paths gets interference. Is there some connection between those two things?
Between what and what?
Between swapping particles giving interference and swapping paths giving interference.
Well, what you're doing is you have two paths for two particles. This path where one goes this way, one goes this way, and another path where they cross over, they sort of wind up the same way. And with bosons, they add. With fermions, they can cancel. So it is connected with interference. But I didn't want to do that now. There is an interesting interference experiment that you can do. But let's come to it later. Okay, that's the tail. That's one minus sign. Now. This sign will come back at us many, many times, but there's another minus sign that has to do not with exchange. This is the minus sign that has to do with exchange of particles. This is the minus sign that has to do with spin, but it has to do with rotation about an axis by 2 pi. Rotation by 2 pi is another process that you might expect does nothing, right? You might expect rotation by 2 pi is a mathematical process that you can imagine in your head, but if you take a system and imagine mathematically rotating it by 2 pi, not grabbing it and rotating it, but mathematically just performing a transformation which rotates it by 2 pi, you've done nothing to it. You've done nothing to it because rotation by 2 pi is just the identity rotation. It's the same as the identity rotation. You think. Or I thought. You may not think. I did think at one time in my life. So you might say, okay, let's now consider a wave function for a particle. One particle now. Psi of x. And now let's rotate our frame of reference. Or, better yet, rotate the particle. I'm only interested in the spin right now. So there's a wave function of the particle. It might depend both on position and spins. Yeah, so we can put some spin, yeah? It depends on whatever it depends on, but in particular it depends on the spin. And now we rotate by some angle. What happens when you rotate a state with a given angular momentum by an angle? Well, an idea? Axis, whatever. An exterior axis. Right, an exterior axis. particle could be located. The particle could be located at the origin.
So this is essentially orbital angular momentum.
No, it's whatever angular momentum it has. Everything. Right. Everything, including the spin, rotation, and so forth. We don't know what the spin is. Spin, no. It could be, yes, it could be rotation about the z-axis. Remember, the spin doesn't have to be along the z-axis. It could be along the x-axis, it could be along the y-axis, it could be along any axis.
So the axis of angular momentum.
Yes, if its angular momentum is pointing in some direction and you rotate about some other axis, the angular momentum could rotate about that axis. But by the time, here's the angular momentum, here's the axis we're rotating about, and we rotate. So by the time we come back by 2 pi, we come back to the same place. So you might expect that if you rotate the wave function, remember rotation,
University.
Harmonic oscillator. Let's just very briefly review the harmonic oscillator because it's going to come up time and time again in what happens from here on in. As I said, harmonic oscillators are ubiquitous. They are all over the place. Anytime you have a system which has an equilibrium state, it could be classical or it could be quantum mechanical, but classical in particular, if it has an equilibrium state and you displace it from equilibrium, generally speaking, it will oscillate. It may oscillate with more than one frequency. For example, a violin